Prabhakaran,
Yeah, present, sir.
Prem Vinayak, Sapish Kumar,
Present, sir.
Satish Kumar,
Present, sir.
Titus,
Present, sir.
Vallish, Vigneshwaran.
Present, sir.
Who is that? Vigneshwaran, right? Vijayaraj? Vijayaraj? Vikas?
Present, sir.
Vivekanand?
Present, sir.
Yadav?
Yes, sir.
Yuvraj? Okay, so there are three absentees, Vallish, Vijayaraj, and Yuvraj.
Yuvraj is joined, sir.
Hello? Yeah. Who has joined?
Yuvraj is joined.
Joined just now.
Okay. Okay, so welcome back. We are in chapter 4. We are discussing instrumentation to study combustion process in engines. So in this chapter, so far we discussed about how to acquire the in-cylinder gas pressure signal using a pressure transducer. We discussed about how to acquire the crankshaft angular position using an optical encoder. We have also discussed about how to get compression TDC position. That is a reference for counting the angle, crank angle. You need a reference for measuring the angle. The standard reference is compression TDC point. So we discussed what are the methods available to get the compression TDC information. Okay, so with this information, you will be able to get the pressure profile, which shows how the in-cylinder gas pressure varies with the crankshaft angular position. This is what is referred to as pressure profile. This is one of the fundamental information you need to have to do the combustion analysis. But pressure profile alone is not sufficient. We need to derive other parameters from the pressure profile, measured pressure profile. So in the last class, I started discussion on how to derive other parameters, important combustion parameters from the pressure profile. By using all these parameters, you will be able to do the combustion analysis in IC engine, both SI and CI engine. Right, combustion analysis plays a significant role. Engine performance improvement or emission reduction is primarily based on the combustion process. So you need to acquire the data and you need to get these various other parameters to do a combustion analysis, and that will help you to find reasoning for engine performance, right? If you want to improve the engine performance, you need to analyze the combustion data, okay, and through that you will be able to come up with strategies to improve the engine performance. Similarly, the pollutants are formed based on how well the combustion event proceeds inside the cylinder. So we need to analyze the combustion event in SI engine. That's the reason we are spending time to know how to acquire the fundamental pressure profile data, and from there how we can derive other parameters. So I will continue my discussion on the parameters that can be derived from the measured pressure profile, which I started in previous class. So one of the information you can directly get from the measured profile is the maximum pressure or peak pressure. So by looking at the pressure profile, you can get the information about the magnitude of maximum pressure value, that is here. Okay, so this is important because this is what is translating into expansion work. Right, so we want to achieve maximum pressure as possible so that we can get the maximum work from the engine. Only during expansion stroke, positive work is produced, and the magnitude of work is dependent on the value of the Pmax. So we intend to have a higher value of Pmax so as to get the maximum work. It's not only about the magnitude of Pmax, it's also about when this Pmax is happening, occurrence of Pmax. So it is here Generally, it is around TDC point after TDC, okay, just after TDC, few degrees after TDC, 5 to 10 degrees is a preferable angle. So it's preferable to have this Pmax happening at 5 to 10 degree after top dead center during the expansion stroke in order to extract maximum work from the gas. So this is an important information we need to note down, and this can be obtained directly from the pressure profile. And second information we discuss is maximum rate of pressure rise, which is dP by d theta. So dP by d theta is nothing but the slope of this profile, and you could see that the slope continuously varies in the profile. And what we are interested to know is the max value. What is the maximum value of dP by d theta? We need to know because we know that the pressurized rate is represented by dP by d theta. When it is too high, it translates into knocking combustion. So we need to keep a check or monitor this value, dP by d theta max value, to see whether it is within an acceptable limit. I said one limit, which is around 8 bar per degree crank angle or around 10 bar per degree crank angle, depending on the engine. That is generally a threshold value above which you can say that the combustion is abnormal or knocking because it's you can hear the knock. Okay, it's audible to human ear that I already discussed. So combustion noise will be high when the pressurized rate is high, but we need to have somewhere optimal pressurized rate, because this is what is again this represents the bond rate, right? Pressurized rate is a resultant of the bond rate of the fuel air mixture, right? So we need to have a better combustion. Better combustion shows a higher bond rate. Okay, it should not be too high from a knocking perspective. It should not be too low also. That's why we need to monitor this value. The other information I discuss is heat release rate. This is apparent. Apparent is an approximate value. It's a net heat release rate, meaning we are excluding heat losses. That's why it is called net value. There are two heat release rate. One is gross and the other one is net. Okay, gross will include the total heat that is released during the combustion. Net will exclude the heat loss. Since you have not insulated the engine, a fraction of the total heat released is lost to the coolant. So when you exclude the losses, heat losses, then you call that as a net heat release rate. So this is a derived parameter. We can derive this net heat release rate from the measured pressure profile by applying first law of thermodynamics. So in the last class, I have discussed this derivation, how we can get this apparent net heat release rate from the pressure profile. Okay, the only information you need to have is the pressure profile to get the heat release rate. And this is done by applying the first law of thermodynamics. First law, you know, it's just an energy balance. So we have done an energy balance here for the closed part of the engine cycle. Closed part of the engine cycle is a period where both the valves are closed. Intake and exhaust valve will remain in the closed position. It means it starts from intake valve closure point. It continues until exhaust valve open point. Until this point of time, both the valves are closed. This is what I mean by closed part of engine cycle. So we apply first law of thermodynamics to this closed part of the engine cycle and do an energy balance, okay, involving various energy terms, including internal energy, work, because of the piston displacement, and then heat loss since we have not insulated the engine, and then the energy associated with the flow of mass into the control volume and from the control volume. So there is a fuel spray in a diesel engine that goes into the control volume. So we say that as a dm with the subscript F and H with the subscript F. H is the enthalpy associated with the mass of fuel that goes into the cylinder control volume. Okay. So this is one mass flow and the associated enthalpy. Another mass flow is the mass that goes from the cylinder to the crevice region. Okay. So we already discussed about this crevice. So there is some mass going into the crevice and there is an associated enthalpy term for that mass. Okay. Which is dmCr. Cr stands for crevice multiplied by H with the subscript Cr. Okay, H is enthalpy of that mass that goes into the crevice. So put together, we refer it as summation of dmi/hi. Okay, compared to the other three energy term, this energy term is negligible, meaning that its magnitude is smaller compared to the other three terms. That's why there is, you can ignore, to simplify the case, we are ignoring that smaller magnitude of energy associated with the flow of mass right into the control volume and flow of mass from the control volume. So this is excluded, okay, considering that its magnitude is low. Then you have the other three term, and what we have done, we have just applied the du term. We expanded the du term through mCv dt, which is a fundamental equation, to get the change in internal energy, du is given by mcv dt, and del w is a PdV work, displacement work, integral PdV. Since it's del W, we can write it as PdV. Okay, and from this we have taken ideal gas equation because we want to get rid of this dT term. Temperature is difficult to measure. Rather, we have already a measured information pressure. So that's what we are doing in the next step. mdt is expressed in terms of PdV by R through the ideal gas equation, and Cv also is expressed in R so as to cancel out this gas constant term in this equation. Okay, so finally from this, if you simplify all this, you get an equation for apparent net heat release rate. Del Q net by d theta is equal to gamma by gamma minus 1 PdV by d theta plus 1 by gamma minus 1 VdP by d theta. So here we are, through this equation, we are estimating the net heat release rate. Why I use the term rate? Because this is expressed in terms of d theta, del Q net by d theta. Theta can be related to time, absolute time through engine RPM. That's why this is called net heat release rate. Okay. Incremental change in net heat release with respect to angle, crank angle, is referred to as apparent net heat release rate. So this is given by this equation. In this equation, you have a pressure term that you have already measured. You have a volume term that you can get from the slider crank relation. I have already discussed about that. And then there is a change in pressure with angle, change in volume with angle. So all these are known terms. Only unknown here is gamma. What is gamma? Gamma is the ratio of the specific heat. So here we need to do some approximation to get the value of gamma. Gamma is a strong function of temperature as well as the composition of the combustion products. And we know both temperature, and so this is a function of temperature. This is also a function of composition. Composition of in-cylinder gas mixture. Okay, so gamma is a function of both because gamma is dependent on Cp and Cv, and both Cp and Cv are strong functions of temperature as well as composition of the combustion products inside the cylinder. So we know with respect to time, temperature varies inside the cylinder, composition also varies inside the cylinder. So gamma, from this perspective, is one of the complex term in this equation, del Q by d theta equation. But nevertheless, over a period of time, people have researched and found that gamma varies in the range of 1.3 to 1.35. Gamma value will be high when the temperatures are less. That is, at the start of combustion, it is typically around 1.35. It's high value. It's closer to air. For air, for ideal, in the air standard cycle, we use gamma value of 1.4. It's the ideal value. Okay. So it will be closer to this value once the temperatures are less. But during combustion, since the temperature increases considerably, there will be drop in gamma. Okay, because of the heat loss. Because of heat loss, the ratio gamma value will drop. So it may be anywhere between 1.26 to 1.3 during the combustion period. Okay, so it varies between 1.35 to 1.26. So you can use any value in between this. Okay, some mean value we are using. Otherwise, you need to consider the effect of temperature as well as composition to get the value of gamma, and that will fall within this range. Okay, it varies continuously, but an approximation is made here. We take a mean value, some mean value of gamma, and proceed with estimating this del Q net by d theta, which is apparent net heat release rate. So that is how we get this derived parameter, apparent net heat release rate, from the pressure that we acquire. Next, we need to know how to get ignition delay time. So ignition delay for SI and CI engine, the definition is different. For a compression ignited engine, diesel engine, ignition delay is the time elapsed between start of fuel injection to start of combustion. In a spark ignited engine, you are not injecting fuel into cylinder, rather you are discharging electric spark to initiate combustion. So here it is self-ignition, here it is spark discharge based ignition. So the criteria is different for this two engine. For SI engine, the time elapsed between start of spark discharge. What is, I will just write down here this abbreviation. So SOI is start of fuel injection. This is applicable for CI engine, and SOC is start of combustion. applicable for both engines. The other abbreviation here is SOS. SOS stands for start of spark discharge. Okay, so these are the abbreviations we have in the ignition delay equation. Start of injection, you know it in a CRDA type fuel injection system, electronic fuel injection system, you know precisely when the start of injection happens. In a mechanical fuel injection system, we have discussed about static timing and dynamic timing. So in a mechanical fuel injection system, you know you have an injector. This is a mechanically operated injector. It's a spring-loaded fuel injector. Whenever the fuel pressure overcomes the spring pressure, the needle in the injector is going to lift and the fuel is going to be sprayed. Okay, so the needle is a spring-loaded needle. It's under pressure due to the spring force. Okay, so when the pressure in the fuel line overcomes the spring force, so you have a spring here. Okay, so that's why it is a mechanically actuated system. So you have a spring force. When the fuel line pressure overcome the spring force, the needle is going to lift, fuel will start to be sprayed into the engine combustion chamber. So fuel spray is based on when the needle lifts. In a CRDA or electronic system, you control the needle lift by energizing the solenoid. So by powering the solenoid through an external circuit, you are controlling the needle lift. Okay, so you are precisely controlling needle lift in an electronic system. This is not the case with mechanical system. Whenever the fuel pressure overcomes the spring force, the needle is going to get lifted. Okay, so it's a mechanical actuation system. Because of this, you have two timings, as I think I have already discussed about this. There are two timings here. One is static timing, that is the time at which the pump open and deliver fuel into the line. So this is a high pressure line we are talking, and that connects pump and the injector. This line connects pump and the injector. Static timing is the time at which the high pressure pump delivers fuel into the line. Start of delivery of high pressure fuel, pressurized fuel into the line, high pressure line, is what is static timing. There is another timing which is called dynamic injection timing. This is the time at which the fuel is delivered into the engine cylinder. So the needle will lift and deliver. The point of delivery of fuel into the engine cylinder is what is the dynamic timing. So there is some time lag between static and dynamic timing. This is what we need to note down here. Okay, so once the fuel is delivered into high pressure line, the pressure builds up here. Okay, pressure is a wave phenomena. Pressure builds up here. It will reach the injector end. In the injector, the needle is normally closed. Once the line pressure exceeds the spring force, the needle will lift and fuel will be sprayed. So that timing is the dynamic timing. Now, in a mechanical system, what do you need to have to acquire this information? So this is the information you need when the fuel is sprayed into the engine cylinder. So this is what I mean by start of injection in a mechanical system. Okay, this information I need to get. To get the information, you need to record the pressure in the fuel line. Okay, this is fuel line pressure. You need to have a device to record pressure in the fuel line. So we have earlier discussed about this fuel line pressure sensor. You could see that there is a sensor, pressure sensor fixed here. This is a strain gauge type sensor. Whatever sensor we discussed for measuring in-cylinder pressure is a piezoelectric type sensor, which should have high thermal resistance because this is exposed to hot combustion gases. Here the temperature is not high in the line, as you know. That's why we use a piezo-resistive type sensor here to record the pressure in the high pressure line. So once you have the device, once you record this line pressure, you can plot this line pressure versus theta. Theta is crankshaft angular position. Okay, so you will get a profile like this. So this is the line pressure variation with respect to crank angle in an engine cycle. What we do here is we will track so pressure start to build up slowly. Once the pressure reaches the nozzle opening pressure, you know, because of the spring force, there is a constant pressure, nozzle opening pressure. Okay, so once the pressure builds up to that value, so this value is nozzle opening pressure. Once this pressure is reached, you draw a horizontal line here, and from there you draw a vertical line. This will meet at a crank angle, and this crank angle is nothing but dynamic fuel injection timing. This is the time at which the fuel is sprayed, start to spray. The injector will start to spray fuel into the combustion chamber at this timing. This is a start of injection. This is how you get start of injection information for a mechanical system. For an electronic system, you know it because the SOI timing is nothing but solenoid energizing time. Of course, there is a small time lag that will be given, okay, based on the electronic system that you use. So you know precisely the start of injection for electronic system. For mechanical system, you have to record line pressure, draw the line pressure versus crank angle plot, okay, track when the nozzle opening pressure is happening, take that associated crank angle as a dynamic timing. So this is how you get start of injection for a CI engine. For SI engine, start of spark discharge, you know. So you are deciding the spark discharge time. Okay, now let us look at how we can get the start of combustion information. There are different criteria followed to get start of combustion information. I will discuss all those criterias. Okay, so one of the criteria is you plot firing pressure profile and motoring pressure profile in the same, okay, the same P theta diagram. You are getting two profile. One is firing profile, firing pressure profile. Other one is motoring. Motoring is unfired pressure. So you will, this is a motoring pressure profile and this is a firing pressure profile. So you know until the start of combustion time, these two profile or the curve will just overlap over each other. So until start of combustion, there is no difference between firing and firing case. Okay, once the combustion start to happen, the firing pressure profile will start to deviate from the motoring pressure profile. So the point of deviation or the angle at which the firing pressure profile start to deviate from the motoring pressure profile can be considered as start of combustion. So this is one of the criteria. I have written here as S4C1. This is one of the criteria used to find the start of combustion time. X-axis you have crank angle. I am tracking the crank angle where the firing profile deviate from the motoring profile. Okay. So this angle is, this is one of the criteria that we use to find the start of combustion. So this is one of the criteria. The second criteria used to find start of combustion is shown here.
This is for SI engine, sir, if I'm not wrong, right?
You can use it both for SI and CI engine.
Okay, sir. Okay, sir.
For both the engines. The second criteria is dP by d theta in y-axis, theta in x-axis. If you do a plot of dP by d theta versus theta, dP by d theta is the first derivative of the pressure profile. You can get dP by d theta from the measured P theta value. You can get the first derivative. Okay. Once you have this value, you plot how this dP by d theta vary with angle, crank angle. If you do the plot, initially there will be some fluctuations. Okay, and then there will be steady rise in the dP by d theta value. The moment or the instant at which the steady rise of dP by d theta is happening is taken as start of combustion. So you know this rise in slope is primarily due to combustion, start of combustion, right? So there will be steady rise in the first derivative of the pressure, and that starting point is considered as a start of combustion. This is the second criteria used to find start of combustion. The third criteria is obtained from the apparent net heat release rate. We have just now discussed how we can derive this apparent net heat release rate by applying first law of thermodynamics. So you plot this apparent net heat release rate with crank angle. Take crank angle on x-axis, apparent net heat release rate on y-axis. I think we have already discussed this profile when we discussed stages of CI engine combustion, if you recollect. So you will get a profile like this, okay? Profile like this. So this is a typical profile, heat release rate profile for a engine, okay, CI engine especially. So because you have premix combustion and diffusion phase combustion. Here the criteria followed is initially there is a dip in the heat release due to thermal energy or heat absorption. We already discussed about that. From the dip, the heat release will start to become positive. So this slope is negative, this slope is positive. The moment at which the slope get converted from negative to positive, moment in the sense angle, crank angle. this angle is considered as start of combustion. This is another criteria. And in some of the textbooks, the slope will rise, and when it crosses the 0 point, so this is a zero point, zero heat release, okay? Once it crosses zero heat release, this is negative value, okay? Generally, they don't consider the negative value based start of combustion. In some of the textbooks, the criteria followed is zero crossover point of heat release in the angle, okay, is considered as start of combustion. Until then, this is negative. Right, start to become positive, you can either take this or this. This is a point where the heat release rate is above zero. So this is another criteria to find start of combustion. And that is primarily used for CI engine, this criteria, okay. The other one is cumulative heat release. Later on, I will discuss about how to get this cumulative heat release. Cumulative heat release is derived from the instantaneous heat release, which we have discussed just now, okay. So from the instantaneous heat release, you will be able to get the cumulative heat release in percentage. So you take this in y-axis, take theta in x-axis. When you plot this cumulative heat release in percentage versus crank angle, you will get a profile like this. This will be similar to mass fraction burn profile. Earlier we have discussed for SI engine, okay, mass fraction burn profile. You could see that the profile is exactly same as that, because cumulative heat release represent the burn rate of the charge. That's why you are getting similar profile. So what we will do here is we will track the angle, crank angle, at which 10% of the cumulative heat release happen, 50% happens, and 90% happen. Right? Let us focus only on 10% heat release now from the perspective of start of combustion. This is considered as the angle at which 10% of the cumulative heat release. This is 10% cumulative heat release. The associated angle is taken as start of combustion. This is one of the criteria. This is generally used for SI engine, either 10%, and in some of the textbooks they also take 5% of cumulative heat release, right? So this is another criteria to determine the start of combustion. I will discuss about the other two terms subsequently. Okay, just here just take a note that this is another criteria. 10% cumulative heat release or 5% cumulative heat release is taken as start of combustion. So you can use any of these criteria depending on whether it is SA or CA engine. I have a question, follow-up question here. Among these different criteria that we use to get the start of combustion, you need to know start of combustion to get the ignition delay. Without start of combustion, you cannot find this parameter. This is an important combustion parameter, ignition delay time. Okay. For that, you need this information, start of combustion. So my question to you, based on the discussion just now concluded, which one do you think is more accurate? Among the 5 criteria we discussed, which one do you think is more accurate to determine start of combustion?
So I think pressure dP upon deta, when it is changing, dP upon deta when it is changing from negative to positive, that is the most accurate. It seems.
We are saying that this is most accurate criteria. Why do you think that this is more accurate?
So because as you have taught us in the previous class that the pressure can be measured very accurately by using crystal sensor, and accuracy of the sensor is very high, sensitivity of the sensor is very nice in that way. So and basically what will happen is when the pressure is changing from negative to positive, that means it is ensured that at that particular instant the combustion is stabilized and it is growing from there. Okay. Whereas other criteria which we have mentioned, like heat release and all those things. So how accurately heat release can be captured, I'm not sure about that, sir. That's why I picked this option actually.
Any other response? All of you agree with this?
Yes, sir. Yes, sir.
Okay. So this is perfect answer. This one is going to be accurate among all other methods we have discussed. The reason is pressure is directly measured. Okay, so pressure based criteria you have two. This is one and this is two. Among this is more accurate because this is dP by d theta. dP by d theta is the first derivative of pressure. So you are going with a fine resolution in dP by d theta rather than p theta. Compared to p theta, dP by d theta will have fine resolution. But both the profiles are from the measured pressure data. Pressure can be accurately measured. Very high precision equipments we have to get the pressure information. This is one of the most accurately measured information data you have about the combustion phenomena. Okay, so you can rely on this because of this. Among these two profile, the criteria 1 and 2, 2 is more reliable because you are resolving more when you take a derivative, right? That's the reason this is accurate. About the other three criteria, heat release rate based criteria, the information is inaccurate primarily due to the reason that you are getting startup combustion from heat release rate, which is a derived parameter from the measured pressure. You are deriving this heat release rate from the measured pressure data. Any derivation, any correlation will have its own uncertainty. For example, just now we discussed that getting gamma value precisely is very difficult because gamma is a strong function of temperature and composition. So you are using this equation to get heat release rate. So this equation has its own uncertainty. Any derived parameter will have its own uncertainty. Okay, so from that perspective, if you calculate or determine start of combustion from a derived parameter, you will have the uncertainty in that due to the parameter that is derived. Rather, if you derive start of combustion from a directly measured parameter like pressure, the accuracy is more. Okay, and among the first two criteria, the second one is more accurate because it's a derivative of the pressure. Clear? Okay, so next one is cumulative heat release. Cumulative heat release in percentage. Cumulative, as the name itself implies, it's you are adding the heat release. That's what it is, cumulative. But you want to express this cumulative value in percentage. So what we will do to get this is obtained from the instantaneous heat release, whatever we have discussed. Okay, so this is the ratio of instantaneous heat release to total heat release. So how do you get this instantaneous heat release? This is the heat release that you get from start of combustion to the crank angle instant at which you want to find the heat release. So basically, you are adding heat release from start of combustion to any crank angle instant. That is what is this numerator term. Denominator term, you are adding heat release from start of combustion to end of combustion. That's the total heat release during the combustion period, start of combustion to end of combustion. Okay, so total heat release is you are summing up all the instantaneous heat release values from the instant at which the combustion gets started to the instant at which the combustion is over. That's the total value. Okay, numerator you have instantaneous value that is from start of combustion to any crank angle. The ratio of these two is cumulative heat release in percentage. So if you plot the data, cumulative heat release data with crank angle, you will get a profile like this. As I said, our focus is on three important terms here in this profile. One is 10% of cumulative heat release, which we use to find the start of combustion. Other one is 50% of cumulative heat release associated crank angle. Okay, so this is so this one is referred to as CA10, which is 10% of cumulative heat release. This is referred to as CA50. This is 50% of cumulative heat release. And then the next one is CA90, where 90% of the cumulative heat release happen. 50% of this is used to find start of combustion. 50% of heat release refers to center of the combustion period, right? This is also called as combustion phasing. So we need to carefully monitor when half of the charge is burned, right? 50% of the charge burn period is CA50. So this is also referred to as combustion phasing. Combustion phasing. This is one of the important terms used to analyze the engine performance because you have to phase the combustion properly so as to maximize the work output from the engine. If it is too early, during the combustion period, then you will have a problem of high negative work. If it is too late during the expansion stroke, you will have a problem of loss of expansion work. So this needs to be an optimal value, CA50 value. So engine closed loop control will monitor the CA50 value so as to get a better combustion phasing to maximize the engine performance. The other one is this is normally considered as end of combustion, the crank angle period at which 90% of the cumulative heat is released. That is what is CA90. This is generally considered as end of the combustion period. Okay, so from cumulative heat release plot, you are getting these three useful information: CA10, 50, and 90. So from this, you will get the combustion duration information, which is nothing but it's a time period between CA10 to CA90. CA10 we are considering as start of combustion. CA90 we consider as end of combustion. The duration between CA10 to CA90. When I say duration, we are considering crank angle duration. Okay, so the crank angle duration between CA10 to CA90 is what is referred to as duration of the combustion event. Did you get what I'm saying?
Yes, sir. Yes, sir.
So these are the useful parameters, and here you could observe that all these parameters, important combustion parameters, the source for all this parameter is the pressure profile. So we have this pressure profile. From this, we have obtained all other important combustion parameters. By using all these parameters, you will be able to do a combustion analysis. So when you say that you are doing combustion analysis for IC engine, SI or CA engine, you need to have all this information in place. When you do experimental work on the engine, when you acquire data from the engine, you need to derive all this important information about the combustion. Okay, and with the data that you have, all the data you have, you will be able to analyze the combustion event in IC engine. Okay, that is the objective here. So with this, I conclude chapter number 4. Okay, chapter number 4 about this instrumentation for combustion process. Okay, so we have discussed various parameters that will help us to do combustion analysis. Now I am moving to chapter number 5. Chapter number 5 is second module. Basically, we have concluded the first module on combustion. So going back to the syllabus we have, so we have concluded the combustion module now, okay, with this chapter on instrumentation to study the combustion process. This first module is on combustion, okay, so we have discussed here starting with the fuel and its molecular composition and its effect on the combustion. We discussed thermodynamic aspects of combustion, and then we discuss actual combustion process in SI and CI engine, including various factors that control the different stages of combustion. And then we discuss about the instruments that are used to acquire the pressure profile, and from there we discuss how we can derive other useful combustion parameters. So with this, module 1 is concluded. The second module is about emissions. You know, emissions from the engine are the resultant of the combustion event. The emissions are nothing but the products of combustion. So in the second module, we are going to discuss about these combustion products. Okay. So these are the contents of the second module. We will start with what kind of products are emitted from the engine. Among the various species emitted from the engine, some of them are designated as pollutants because of the health effects it creates. So we are going to discuss about what are those pollutants emitted from engine, what is the mechanism at which these pollutants are formed, and then we will discuss about the various factors that influence the pollutant formation in SI and CI engine. Once we identify factors, we will devise suitable control measures to reduce the pollutants, okay, from SI and CI engine. We will also discuss about instruments that are used to measure the concentration of pollutants emitted from the engine. The final chapter is about emission standards and testing. So until this point of time, if you look at the contents, the way it is phased, it is just resembling the first module content, wherein we started with the discussion on characterizing combustion event, then bring out the factors that influence this combustion event, and then we discuss about the instrument. Similar sequence of contents are followed here for the second module. We discuss the mechanism at which the pollutants are formed. Then we will bring out the factors that affect or influence the pollutant formation in SI and CA engine. Okay, after that we devise control measures or control methods to reduce the pollutant. And then we discuss instruments to measure the pollutant concentration. The last chapter is about what are the current emission standards, right? And how do we get the information about the emission standard, in the sense that, you know, currently we are following BS6. Okay, for each pollutant there is a limit, concentration limit. So we need to know how we can measure those concentration, what kind of methods or testing you need to carry out to get the pollutant concentration based on the standards, emission standards. So this is what we are going to discuss in the final concluding chapter. Okay, so this is the first chapter of emission module, and it's also fifth chapter, okay, from the continuous sequence. So what we are going to see here, we are going to discuss about pollutant formation in SI and CA engine and factors affecting emission. So here we are going to look at the types of pollutants emitted from IC engine. So, you know, as a resultant of combustion, this is where the objection is coming in to use electric vehicle more recently. So we don't want the engine to emit various species into ambience, because some of these species are designated as pollutant. They are designated as pollutant because they create several health effects to the human beings. Okay, some are immediate health effect and some are long-term effect. You don't know when it will pop up. This effect will pop up. Okay, some are immediate. Right, once you inhale the pollutant. So what we are going to see here are what are the species that are designated as pollutant, what effect it create on the human health. I'll briefly talk about health effect. This is exactly the reason why they are categorized as pollutant. So we need to know what effect it creates. Okay, this is where the objection is coming in terms of using IC engine based vehicles. Okay. Then after this, I will discuss about the sources. What are the sources for the pollutant formation? These sources are going to be different for spark ignited engine and compression ignited engine. So I will discuss about the various sources that result in pollutant formation in these two IC engine categories. Okay. After that, I will discuss about the mechanism, pollutant formation mechanism. Okay. So it's very important to understand the mechanism, because it will help you to bring out the factors. Once you have an understanding about the pollutant formation mechanism, you will be able to identify engine design or operating variable based factors that will influence this pollutant formation. Once you understand how these pollutants are formed and what are the factors that influence this pollutant, it will help you to come up with suitable mitigation strategy, pollutant control strategy that will be discussed in the next chapter. Okay, so this chapter is devoted to understand what are the species designated as pollutant, what health effects it create on the human being. Okay, what are the sources for the pollutant formation in engine, what is the mechanism upon which the pollutants are formed, and finally we will discuss about the factors, engine design and operating variable that influence the pollutant formation. So to start with, here I have provided an overview of SI and CI engine emission. So this is an overview of spark ignited and compression ignited engine emissions. So emissions from engines, IC engines, SI and CI engine, can be categorized as two broader types. One is engine tailpipe emission. Tailpipe is an exhaust pipe through which the various species are let out from the engine to the surrounding ambience. Okay, so electric vehicles have zero tailpipe emission, but there are some other problem as we have discussed. Right, the power, electric power we get from in India, it is mostly from coal. Okay, so you use a high carbon source to produce electric power. That is where the objection is on electric vehicles. So we need to do a complete life cycle analysis to track the source for producing electric power. Right, although tailpipe emission is zero in a EV electric vehicle, you have a power source, electric power source, that is highly pollutant based source. That's why it's important to do a complete life cycle analysis, track the origin for the electric power. So of course, in an IC engine, you will have a tailpipe emission. This is where the objection is. So engine emits as a resultant of combustion engine emits various species into surrounding ambience, okay, we categorize them as tailpipe emission. This is one category. The second category is called evaporative emission. This is more harmful. The first one is more harmful than the second one. Nevertheless, this is another category, evaporative emission category. What are this evaporative emission? Evaporative emissions are primarily due to vaporization of the fuel, especially with a high volatile fuel like gasoline. You will have more evaporative emission. The sources are, this can happen from the fuel tank, this can happen from the crankcase vent, this can also happen from carburetor vent if you use a carburetor engine. Generally, this is not used now, we go with PFI, okay, but still some low cost SI powered vehicles use carburetor, okay. You have a vent in the carburetor, through that the fuel vapor will be let out into atmosphere, and fuel is an objectionable, fuel itself is a pollutant because some of the hydrocarbons in the fuel are dangerous for human health. I think I already discussed about this in the first chapter. For example, if you take gasoline, it has more aromatic, around 30% aromatic. Any aromatic, anything with a benzene ring is carcinogenic. It has a potential to cause cancer. Any benzene ring based, okay, so this is a benzene ring. Any hydrocarbon with a benzene ring has a potential to cause cancer. This is a carcinogenic hydrocarbon. So when the fuel is let out into atmosphere, fuel vapor is let out into atmosphere, okay, it is also creating a health problem, and those are categorized as evaporative emission. This is where I said when you go on fuel your motorcycle, gasoline, if you open the tank, you could smell the fuel, right? As soon as you open the tank, right? So here you have to be careful because you don't know what hydrocarbon you are inhaling. When you take in, when you inhale, you are taking in the hydrocarbon into your body, okay? And some of these hydrocarbons are objectionable hydrocarbons. So that's why you should avoid inhaling this hydrocarbon. Beyond a threshold value, our body can tolerate up to certain limit. Beyond a threshold value or limit, it's going to show up its effects on the health, okay? So from the fuel tank, especially when you refuel your vehicle, you will have evaporative emission. You will have a vent in the crankcase. You will also have a vent in the carburetor. Through this also, you will have emissions coming out. Carburetor and fuel tank based evaporative emissions are most common in SI engine because we use gasoline. Gasoline is highly volatile. Diesel is not as volatile as gasoline. We know that because of heavy hydrocarbon. So this problem will be there in SI engine because of gasoline, which is highly volatile. It's a highly volatile fuel. It is not severe in diesel because of heavy hydrocarbons present in diesel, but the carburetor vent based emissions are common in both SI and CA engine. Now let us look at why there is an emission from the, sorry, not carburetor, crankcase vent. Now let us look at why there is a hydrocarbon emission, evaporative emission from the crankcase vent. Okay, so crankcase, you know, it's located at the bottom end of the engine. Okay, so here you have high pressure combustion gases. The pressure is so high here and the pressure is low here in the carburetor. So you have a delta P that naturally exists between the two ends. Piston is acting as a sealant. Piston is in fact sealing the high pressure combustion gases from reaching to the crankcase. Otherwise, you will have a gradient, delta P gradient, that allow the gases, including fuel vapors, from this end to go this end. Although piston is sealing, perfect seal is impossible to achieve. So you have something called blow-by. I think I already discussed about this blow-by. You have some high pressure gases leaking through the radial clearance between the piston outer surface and the cylinder liner. Okay, since you are providing some clearance to account for the thermal expansion of the piston, otherwise you will have a problem of running the engine. Piston will get stuck with the liner, it cannot even move. You need to account for thermal expansion based on the material you use to construct the piston. So you have a radial clearance and you have a delta P. The combination of this results in blow-by, wherein the gas, high pressure gas, leaks from the combustion chamber. It goes all the way to the crankcase. Okay, this is blow-by, and what this gas will have, it will have fresh mixture, it will also have fuel vapor. Okay, it will have everything. Okay, will build up in the crankcase, so you have to release this pressure. That's why you are providing a vent here. Okay, If this vent is let out into atmosphere, you will have a problem of releasing vapor into surrounding ambience, which is what is an evaporative emission. So you need to avoid that. Okay, to generally the general practice is you will connect this crankcase vent to the intake manifold. Okay, so that the vapor is recirculated back into the engine itself. You are not letting out into atmosphere, but you need to note down here that this is one of the source for evaporative emission. You need to carefully connect it to the intake manifold to avoid that. So blow by exists in both SI and CI engine. You cannot do a perfect sealing. Piston cannot perfectly seal the high pressure gases from leaking out to the crankcase. The fuel vapor. Once it reaches its threshold value, you can purge air to release the vapor into intake system. This is generally followed to avoid this problem of evaporative emissions. Okay, so you have these two sources of emission. One is evaporative, other one is tailpipe. Tailpipe is more problematic compared to evaporative emission. Which can be easily addressed as I just now discussed. Tailpipe emissions include pollutants. Tailpipe emissions are nothing but combustion products, okay, which include some of the species are pollutant. You have two pollutant category. One is primary or regulated, other one is secondary pollutant. Primary pollutants are also called regulated pollutants or criteria pollutants because the value of this species is checked and regulated by a emission certification agency. In India, we have this ARAI in Pune, which is an emission certification agency. Okay, the concentration of these four species needs to be checked before a new vehicle is launched into the market. And there are standards across in each country. There is a own emission standard. We have BS6 from April 2020. So these four species, unbound hydrocarbon, carbon monoxide, oxides of nitrogen that include NO and NO2 put together. So X is 1, 2. Okay, NOx, oxides of nitrogen, particulate matter. These four species emitted from the engine tailpipe are designated as regulated or criteria pollutant because of the various health effects these four species cause. Okay, I'm going to discuss about that in the next topic. And the other category of pollutants are secondary pollutant. These pollutants are formed from the primary pollutant. They are primarily ozone and NO2, right? So NO2 emitted from the engine when it is released into surrounding ambience in presence of UV, ultraviolet rays, it forms NO and O. O is radical, you know, it's highly active. It combines with oxygen in the atmosphere and form O3. What is O3? Ozone. This ozone is again highly reactive. It reacts with NO release from the engine and it start to form NO2. So we could see that there is a concentration of NO2 building up and ozone also building up in the ground level. Okay, ground level ozone is dangerous. It's also one of the pollutants. Okay, the source for all this is NO2. In presence of UV light, it's forming all this. So some of the species released from the engine are forming other pollutants in the surrounding ambient. Those are secondary pollutant. One is ozone that you get, and NO2 in presence of volatile organic compounds. Volatile organic compounds are example is benzene. In presence of volatile organic compound, NO2 will form photochemical smog. If you have high NO2 concentration in the surrounding ambient, which is forming through this route, right? In presence of volatile organic compounds, this is also released by engine, especially SI engines release more volatile organic compound. This NO2 and volatile organic compound combine and form this photochemical smog. What is this photochemical smog? Any idea?
Sir, the acid rain is the acid rain I've heard. So probably.
So you would have observed lack of visibility under certain conditions, right? In some seasons where NO2 levels, if at all it is very high, you could see that there is no visibility on the road. It caused a lot of accident, right? So you might have heard in the news about the smog. Smog on the road surface will obstruct the visibility. You cannot see what is going on ahead of you when you are driving. Okay, so this is called smog, and this smog in the ambience is dangerous, and this is formed from NO2. NO2 and volatile organic compounds combine and form a white haze, a cloud kind of thing on the ground level. This is what is a photochemical smog. Okay, it obstructs the visibility and it may lead to accidents. Okay, on the road, especially when someone is driving the vehicle, because the visibility is completely obstructed due to the formation of this smog. And this is one of the secondary pollutant. So primary pollutant released from the engine tailpipe leads to other pollutants that are formed in the ground level itself. Ozone, NO2 and smog are formed in the ground level itself. The source for this is the primary pollutant. Okay, that's why these are categorized as secondary pollutant, which are formed from the primary pollutants. It's time up. I stop here. If you have any questions, I can take them.
Crank vent, you mentioned that there will be a connection to the inlet manifold, right? Or the fuel line, the high pressure line. So will there be
not a fuel line? It is connected to the manifold, intake manifold.
Yeah. So will there be chances that it should be like a one-way constraint, right? Or because if there is if there's a sufficient stroke in the cylinder, will there be some kind of a pull into the crank vent directly or something like that from the manifold?
No, manifold is subjected to engine suction, right? Manifold is subjected to engine suction only during the suction period. If you have a suitable blow by gas during that period, it will be taken in.
But in the next stroke, like when we have the compression stroke, there will be less pressure on the crankcase. Will there be chances that air from the manifold comes into the crank?
No. That pressure gradient won't exist.
Okay.
That reverse flow you are talking, it won't exist.
Okay.
The engine suction side is always at a lower pressure, and engine suction effect is felt only during the intake stroke.
Okay.
Rest of the time, it is like a normal ambient condition.
Okay.
Okay, I'll stop here. I will see you on Monday, 6 o'clock. Thank you.
Yeah. Thank you.
Thank you so much, sir.
Thank you,
sir. Thank you, sir.
Thank you. Bye.